TOF-MEIS uses multiple detectors. The upper detector is used to measure random or channeling spectrum with backscattering experiment. The lower detector is mainly used to measure hydrogen using elastic recoil detector analysis. In short, it is called ERDA. A random spectrum is obtained when all atoms in the sample are exposed to an incident ion beam with the same probability. In this way, the compositional depth distribution can be analyzed. Because the atoms in an amorphous sample are randomly present within the medium, almost all the atoms are equally exposed to the incident ion beam at any angle. The random spectrum can be obtained by measuring it from any incident and scattering angle. In contrast, in crystal samples, the atoms are lined up side by side. Therefore, when viewed from a certain angle, all atoms except those in the surface atomic layer are hidden by the surface atoms. Therefore, a random spectrum cannot be obtained when irradiating the incident ions in this direction. However, even for crystal samples, the angles at which the atoms of the crystal can hide are limited to a few angles. Therefore, if the crystalline sample is continuously rotated at a certain angle, all atoms are exposed to the incident ions with the same probability. Thus, a random spectrum of the crystal sample can be obtained. MEIS K120 can acquire a random spectrum of a crystal sample at a desired position by continuously rotating using the X, Y, Z, and 3 rotation axes. Because the atoms of the crystal samples are lined up side by side, when viewed from a certain angle, all atoms except those in the surface atomic layer are hidden by the surface atoms. Therefore, when the incident beam is irradiated in the lattice direction of the crystal, it is scattered only from the surface atoms and atoms that are displaced from the crystal lattice, and the spectrum measured in this manner is called a channeling spectrum. Therefore, by measuring the channeling spectrum, the depth distribution of the elements that are displaced from the crystal lattice can be analyzed. Using channeling spectrum, the spectrum of the element overlapped with the substrate's spectrum can be clearly recognized by reducing the spectrum height of the substrate. In addition, the substitution ratio of a dopant can be obtained. For this, first, the total number of dopants is obtained through random spectrum measurement. Then, the number of interstitial dopant is analyzed by channeling analysis. By comparing the difference between the random spectrum and the channeling spectrum, crystallization information of the sample, such as the substitution ratio, can be obtained. In the case of a crystal sample, when the lattice direction is toward the detector, atoms except those in the surface atomic layer are hidden behind the surface atomic layer and are not visible from the detector. Therefore, particles scattered by hidden atoms and flying towards the detector cannot reach the detector because they are blocked by other atoms. When the detector orientation deviates slightly from the crystal lattice orientation, the atoms beneath the surface atomic layer become visible. Consequently, the scattered particles can safely reach the detector. Measuring the scattering yield of scattering particles as a function of the angle near the lattice direction of the sample is called the blocking dip measurement. The scattering yield is the lowest where the detector orientation coincides with the lattice orientation. The scattering yield gradually increases as it deviates from this direction to form a dip called a blocking dip. Because this blocking dip indicates the lattice direction of the sample, the position of the blocking dip changes when the lattice constant is changed by strain. Therefore, the strain depth profile can be analyzed by measuring the blocking dips at their respective depths. MEIS analysis mainly uses backscatter measurements. ERDA or forward recoil scattering measurement for special purpose are also used. ERDA stands for Elastic Recoil Detect-on Analysis. This method detects target atoms recoiling directly at scattering angles of 90th or less via elastic collisions. This method can be used to measure atoms lighter than the incident ions that are not measured in backscattering experiments. Because recoil particles are also generated by elastic collision events, the surface energy is determined by the kinematic factor, Kerr. The scattering energy is reduced as a function of depth by the stopping power, and the recoil cross-section is already well known. This can be used to measure the quantitative compositional depth distribution of lightweight atoms. The light element recoil particles have a low scattering yield, and their energy is also lower than that of the scattered particles. Hence, they are buried in the other spectrum of the energy spectrum and are not easily visible. Therefore, additional tools, such as a mylar film, should be added to analyze recoil particles. In comparison, a light element recoil particle reaches the detector earlier than a scattered particle in TOF-MEIS. This is because the flight speed increases in inverse proportion to the square root of mass. Therefore, the recoil spectrum is naturally separated from scattered spectrum. If ERDA is measured by the TOF method using helium ions, recoiled hydrogen can be analyzed without a filter in the 20 nanometers thick region of the sample surface. Thus, this method has an excellent detection limit and depth resolution compared with other RBS type equipment.